Hi everyone, my name is Tianyu and today I want to talk to you about the Zen of Git. Since I've got a lot to get through and not a lot of time, I'm going to jump straight into it. When I started putting the slides together for this talk, I came across this parody of the Zen of Python. It's also called the Zen of Git. Now, someone was expressing their frustrations with using Git and they wrote things like, ugly is better than beautiful, complex is better than simple, readability is meaningless, errors should never be comprehensible, there should be no obvious way to do it, although there may be endless non-obvious ways to do it. If this sounds eerily like your experience using Git, have no fear. Today I want to tell you the real Zen of Git. But in order to do that, I need to start right at the beginning. In the 17th or the 18th century, there was a town called Königsberg, and this town was known for a famous mathematical problem called the Seven Bridges of Königsberg. And the problem asked whether or not it was possible to cross each of the seven bridges exactly once. A mathematician by the name of Leonhard Euler managed to prove that you actually could do this. And the way that he did this is interesting to us. So first of all, he drew each of the seven bridges as lines, and then he drew the land masses that these bridges joined as these blobs here. If I remove the picture of the town from the background and I redraw those blobs as circles so that they are uniform, we end up with this object here. Now, this object is a graph, and it consists of simply nodes and edges. And you might be wondering what the applications of this are, but there's actually a whole field of mathematics that's dedicated to the study of these objects and their properties, and it's called graph theory. Now, why on earth am I talking to you about all of this stuff? How does this have anything to do with Git? Well, let's first look at a more concrete example of a graph, and then we'll talk about Git. So if you think about a social network, and I'm sure probably most of you, if not all of you, use at least one social network. If you take Facebook or LinkedIn, for example, everyone can be represented using a node. And you can represent the connections between people using edges, right? So I can have friends or LinkedIn connections, and I can depict it like this. And all of my friends can have their own friends, and you can imagine this goes on and on and on, and you have all of these nodes and all of these people being connected. Now what I can also do is I can draw arrows instead of just having the line. So previously when we just had a line, we indicated essentially a two-sided relationship. The connection will only be formed if both you and the other person agree. In the case of something like Twitter, for example, I can just follow anyone and anyone can follow me, and that's it. Like there doesn't need to be a bilateral agreement. So in this case, we represent the relationship using an arrow. So if I follow someone, my arrow points to them, and if they're following me back, there will be another arrow that points back to me. So this is also a graph, even though the edges are arrows. And the name for this special kind of graph that has these types of edges, is called a directed graph. Which brings us to Git, because conveniently enough, Git is actually one of these directed graphs, and the way that Git stores commits and all of the files and all of those things in your repository is using this directed graph structure. So now that we've seen this, let's actually see how Git actually does this. Let's say we're starting off with a very small directory structure like this, and we're going to make a commit to Git for the first time. So this is going to be our first commit. The first thing Git is going to do is it's going to create what are called blob objects that correspond to each of the files in our repository. So in this case, we only have three files. We have index.js, index.html, and readme.md. So Git is going to take index.js. It's going to prepend a header that consists of the word blob and then the size of this entire thing. And obviously followed by the contents because we're prepending the header. And then it's going to take the entire thing, the header plus the contents, run it through the SHA-1 hashing algorithm, and then end up with a hash. And this hash is going to be the file name of the file that contains all of these contents. Git is then going to do a similar thing for the other two files, so those are also blobs. But note that we haven't actually stored the file names, for example. We've just stored the contents. So that's where, and neither have we stored any folders or anything like that. So that's where the next type of Git object comes in, and that's called a tree. So what does a tree look like? Well, again, we have the header that indicates what it is. So in this case, we have the word tree to indicate that it's a tree. And then the rest of the tree object is going to contain one line for every single entry, if you like, in that folder. So right now we have the tree object for the JS folder, and we know that JS only has one file, index.js, so there's only one entry there. And the key things to note here is the fact that you have an association between the hash of the file that contains the contents of index.js and the actual name of the file, which is index.js. So this is how Git is actually able to associate the blobs with their actual file names. Right, so moving on, if we also want to look at what the object for source looks like, just to make sure we really understand, again, we have the header, and then we have an entry for index.html and a tree entry for the JS folder. And again, there's always going to be one top-level tree that represents essentially the starting point for our entire repository. So there's obviously going to be another tree object that's going to be constructed in a similar manner. Now, we haven't said anything about commits yet, and we're making a commit. So where does the commit object actually come in? So this is a perfect time to introduce it. And when we make a commit, there will always be a commit object that is created. And just like tree and blob objects, we have the header that says commit. The other thing that's interesting to note is that there is also it's followed by a line which indicates the top level tree at that particular point in time. So using just the top level tree, we can actually reach all of the subsequent trees and blobs. So that's why we only need to store just that one top level. And then the rest of the commit object is pretty much familiar to anyone who has used Git log before, which is probably everyone. So that's what a commit object looks like. Now, you can think of, obviously we have all of these objects here, and you can think of the way that Git actually has references to other objects by using their hash as actually implementing this kind of directory graph structure. And that's exactly what Git is doing. So just to make sure that we really understand what's going on here, let's look at another iteration of this. So let's say that I decide to make two changes. So I'm updating the README file and I'm adding a new file called gitignore. So in this case, because the only two things that are changed are the new contents of readme.md as well as the new file of the gitignore, Git is only going to construct the two new blobs that correspond to these changed files. All of the other blobs and trees stay exactly the same. Well, all of the ones that are not referencing these are staying exactly the same. So in this case, because the top level object, the top level tree contains readme and gitignore, the top level tree also needs to be updated because it needs to have new references to these new blobs. But the trees for source and JS and the blobs for index.js and index.html stay exactly the same. And again, because we have a commit, we also have to create the top level commit object, and then the rest of the references are simply reused, like so. Now, the only difference now when we're making a second commit as compared to the first commit is that the second commit is going to be pointing to the commit that came before it. So we have a final reference like this. And just to make sure we really understand this, because this is really key to understanding Git, let's have another look at another change. So let's say that I decide to make a change to the index.html. So I think by now we all know that because index.html is the only thing that changed, we're going to create a new blob that contains the new contents of index.html. And because the index.html is inside the source folder, we now need to regenerate the tree object that corresponds to source, like so. But everything else, so the JS folder, the readme, the gitignore, those stay exactly the same. And because the source folder is inside the top level always needs to be regenerated. And finally, we have the commit, and then we simply reuse all of the other references, like so. So this is how Git works as a graph. Now let's look at some extra metadata that we can put on top of the graph to help us reason about where we are. So let's say I have this sequence of commits, and we know by now that each commit has a top-level tree associated with it, and that top-level tree can point to any number of subtrees and blobs, and some of them might be pointing to blobs and trees that were created in previous commits, like so. Now, if I decide to stick something like I can think of it like a landmark, or sometimes I can think of it like a post-it note. But let's say that I decide to stick these two landmarks. One I call checkpoint and one I call testing. Now, what I can do with these is that I can move them, or I can take them along with me as I make commits, right? So let's say that I make a new commit here and I take the testing with me. And so I essentially have this this signpost that I'm taking with me as I'm making commits. And that helps me to know where I am, and also allows me to go back to or travel to another signpost if it exists, right? And this is actually exactly what a branch is. So a branch in Git is simply one of these signposts that allow you to know where you are. And Git also does the updating of it automatically for you. So you don't need to remember to update your signpost to the new commit once you've made the new commit. Git just simply does it automatically. And how is it actually implemented? Well, a branch is simply a file on disk. The name of the file is the name of your branch. And then the contents of the file is simply just one line that contains the SHA-1 hash of the commit that the branch is on. So, and that's it. There's nothing more and nothing less. So you can see that branches are actually very lightweight things. And when you move around, or when you update a branch, you're just updating one line in a file. Right. So that's a branch. Then there's another special piece of metadata called head. And head is really like, the way I like to think about head is it tells you where you are inside the graph. Because you can imagine as this gets bigger and more complex and there are more signposts and more things, you need to like have some way of knowing exactly where you are, because you might not always be at the newest point. You want to also be able to travel to previous commits. So head simply just tells you where you are, and usually head is pointing out whichever branch you're on. And even though head is not a branch, it's implemented just like a branch in the sense that it is a file on the disk with the name capital HEAD, and the contents of it contain either a branch name or a commit name, if you so happen to be on a commit. The other useful thing about head, apart from telling you where you are, is also to disambiguate between different checkpoints. So let's say, the landmarks, signposts. So let's say that you have two or more signposts that are pointing to the same commit. How do you know which of those you're actually on? Because you can only be on one branch at a time. Well, again, in this case, head is used to disambiguate between the two. Like so. And we can also use this framework to think about tags, which are just like branches, except that they don't move. They simply just stay at a commit. And also remote branches as well. So all of these are examples of metadata that sit on top of the objects that are in the graph. And Git also, another word for this, or I guess maybe the official word for this in Git is these are called references, as opposed to the objects that we saw in the graph. Okay, so now that we've seen this, let's have a look at some common Git commands in terms of this framework. Let's say I have this particular structure. So I have this sequence of commits here, and obviously we know that these point to trees and blobs, but I'm not going to draw those for the sake of simplicity. And this is setting up the scenario. So we have two branches, feature and test, that have diverged from master. And because head is pointing to test, that means we're on the test branch. Now let's look at some commands. So if I run git merge feature in this case, what Git is going to do is it's going to create a merge commit that contains two arrows. So in this case, it's going to point to the branch that I'm currently on, which is test, as well as the branch that I want to merge, which is feature. And this merge commit is going to join the two ends of those branches together. And then finally, because I'm making a new commit, the branch pointer gets updated. So at the end of this, if I look at the test branch, I'm able to access all of the commits that used to be on the test branch, as well as all of the commits that are on feature. So that's how a merge looks. What is rebase? Rebasing does something slightly different. So in this case, I'm going to take the commits that are on test, but that are not on feature, which is where I'm rebasing onto, and then I'm going to replay or redo those changes one commit at a time on top of the place that I'm rebasing onto, in this case, feature. And after this process, my branch pointer is going to get updated to the new commit there. So you can see in this case, we have essentially duplicated the two commits that used to be on test. And that's really important to note. So by the end of this process, the changes, so the files look exactly the same, but the Git history looks different because of the fact that we've duplicated the commits. Checkout is quite a different thing altogether. And let's have a quick look at checkout. So checkout, I generally like to think of it as you're able to move around or travel in time in the Git graph. So in this case, right now I'm on test. If I were to check out to master, all that happens is that the contents of head change to point to master. And that's the main feature of checkout. Obviously it does a whole bunch of other things, but in this case, this is what we care about. Now I can also check out to a specific commit, and this is fine. And although people do get confused sometimes because they think maybe if I check out to this commit, maybe it's going to check out to the branch that is actually pointing to this commit. Unfortunately, that's not actually the case. If you specify a commit ID to checkout, Git is going to move head to exactly that commit, regardless of if there are other branches or tags there. And what Git is going to tell you at this point is it's going to be like, oh, you have a detached head, you might lose your work. And people often get a little bit concerned about this, but the only thing that this is telling you is that if you decided to make a commit here, like I am doing here, and then at some point I decided to move away, so if I check out back to master, then that commit that I've made, EE2DF5, I can no longer get back to it because there's no branches or tags pointing at it. So Git, that's all Git is telling you that to be careful of. And if you want to avoid it, you just need to create a branch there. Because once you have a branch, you have a signpost that you can easily go back to. Now, reset can also be confusing to some people, and I like to think of reset as, so whereas checkout updates the head pointer, reset simply updates the branch pointer. And leaving head staying exactly the same. So if I do git reset feature here, my test branch pointer is going to get updated to exactly what feature was pointing to, but head is still pointing to test. So what I've done here is I've essentially made my test branch look exactly like the feature branch. So we've covered a lot of stuff, and there was a lot of stuff to cover, and I had to go through it very, very quickly. But you can see that you can think about commits kind of like in this way with these objects and using nodes and these directed edges. And we also know that underneath each of these commits lies a top-level tree object that points to any number of subsequent trees and blobs, right? And we know that on top of these objects, we can also place references or essentially metadata that help us to reason about and navigate around the graph. And finally, we were able to look at some sometimes commonly confusing commands using all of the stuff that we looked at previously. And I would say that this is the Zen of Git. This is truly the essence of understanding Git. And if you're able to understand this, I guarantee you will enjoy using Git so much more in your day-to-day work. And I really hope that you would take this chance to absorb the information and explore using Git for yourself, because I think it is a very, very powerful tool, and it's really great that we can actually use it. So thank you very much. I would love to hear any questions or comments that you might have. You can find me on Twitter, and enjoy the rest of the conference. Thank you.
Yay! Thank you so much for that talk.
Hey.
That was amazing. Yeah,
Thank you very much. I really enjoyed making it.
Yeah, so many people in the chat are just like, I need to watch this 10 times, and I'm sharing this with everyone I know. And they are not alone in that.
Okay,
I
yeah.
think I've used rebase, but I don't think I ever fully understood what was actually happening under the hood there. So that was really useful and helpful. So thank you so much for that.
I'm really glad. You're really welcome.
So we do have a few questions in the audience, and the one that I think we're all the most curious about is what is the worst Git scenario that you've fixed without just completely recloning the repo? Because I think most people have been at that just I'm going to start completely over phase of recloning.
Yeah. Yeah, so I know we only have a couple of minutes, so I'm going to keep it short. But when I was working at Booking, there was a situation where one of the teams who weren't super technical, but they were still using Git, they had committed some, let's say, sensitive information in the Git repository. And this was
Oh
like a
no.
while back. So they did it, and then they had all of these commits that were made afterwards. So it wasn't it wasn't really straightforward to just like undo that one. So when we actually figured out what the problem was, we ended up having to rewrite the entire history from that point using the filter branch command, which is something that you don't use very lightly. And
Yeah.
that, as well as coordinating with the GitLab, because we were using GitLab, coordinating with the GitLab admins to actually remove also the objects from the server side as well. So, and also, so it was running the filter branch command on one copy of the repository and then force pushing that one all the way up, and then asking everyone to essentially get it from that point instead of having to pull. So it was like quite a coordinated effort, but we managed to do it
Oh my gosh.
without too much trouble. Yeah, that was probably the scariest one that I remember doing in recent history.
Yeah, I'm like I felt my eye twitch just a little bit just thinking about all of the
Yeah.
intricacies of having
Um,
to make sure every commit is in place and nothing actually breaks. Oh my goodness.
mhm.
Oh, well,
Yeah,
good
that's why I
job
think it's
doing
really
that.
important to understand what's actually happening so that
Yeah,
you know exactly the command that you should actually run for your scenario. Yeah.
right. Oh, for sure. And so another question that a few people actually asked is what else is the checkout command doing in addition to just updating the head content?
So I guess it depends on which invocation of checkout you use. So if you just
Mhm.
do git checkout and then give it a reference, it's going to just update the contents of head to that reference, whether that reference happens to be a hash or it happens to be a branch or even a tag. Um, there are other, like I'm sure people know that you can also create branches using checkout. You can also essentially change the contents of specific files using checkout as well. So I would say it depends on which invocation you're using, but fundamentally
Sure.
you're still updating head, even if sometimes head doesn't actually change, but Git is like, okay, you're updating head to where you are right now. So yeah.
Gotcha. That makes a lot of sense. Yeah. And there's one other one where I think not just here, a lot of developers deal with is rebasing versus merging and kind of being
Hmm.
confused as to the difference between them. And you talked a lot about the difference already, but are there ever scenarios where you can use both, but you choose one for a specific reason?
I would say there are quite a few situations where you can do both. For example, if you're working on a feature branch and maybe you created that feature branch a while ago and you want to get the latest changes from the main branch. So in that case, you can either merge in the main branch or you can rebase on top of the main branch. And both are like you end up with the same changes in the files at the end of the process. But if you wanted to, like I generally prefer to rebase onto the main branch to actually update my feature branch. And that's just because I like keeping my branch in a straight line because I'm just applying the changes on top rather than having the situation where I'm
Sure.
joining the ends together. Yeah. But in the case of, for example, where you have all of the changes on your branch and it's ready to go into the main, in that case, I would say you should merge because rebasing in that situation you can do, but generally you wouldn't do it unless you're the only person who's working on that repository and you know what you're doing. So, yeah.
Sure. Cool. Well, thank you so much. This is so helpful and so practical. And
you.
again, this is a talk that I think a lot of people will be rewatching. So thank you again for being here today.
Thank you. Thanks for watching. Thanks for the lovely questions. And yeah, enjoy the rest of the conference.
Great. Well, up next, we have Scott come in to speak. So here we go.